All right, we're into some more integration now. So remember when we learned derivatives, we learned like how to take the derivative of just a really simple monomial function like x cubed. And then we said, well, what if we take the derivative of something like x cubed plus 5? And we learned how to do the sum of monomials, which would be, a polynomial of some sort, like a trinomial. And then we talked about those rules for the times when we don't just have one term, when we have more than one x in each term. So something like x times the square root of x, or something like that, or the square root of x minus 1, where we can't really just do algebra and get them down to like a polynomial, that we have to do something else. Then when we were deriving, we had to do the chain rule and the product rule. And so, as you might imagine, with integrating, we have to do something also, because there is, we can't just say like, oh, they're multiplied together, it must be the integral of this and the integral of that, because it just doesn't work that way, right? Because we know derivatives don't work that way, so integrals couldn't work that way since they're inverse operations of each other. So there's this thing in integration called the reverse chain rule. And we're going to talk about it. And then we're going to talk about U-substitution. And let me tell you, I'm such a geek. U-substitution is like literally one of my favorite things in calculus. I think it might be my favorite. I just love it. I don't know why I love it. I don't know why I'm such a geek about it. But I just love U-substitution. It's so cool. So hopefully you love it too. And the general power rule we'll kind of talk a little bit about, but know that it's really just a special case of U-substitution. So if the general power rule doesn't sit well with you, that's totally fine, because it's just U-substitution, and you could just do U-substitution every single time. You would like never have to do the general power rule if you don't want to. But some of you might see it really well, and it might be like it's a kind of a shortcut because you don't have to do the extra sub in that you might have to do otherwise. So let's take a look at that. So the general power rule for derivatives is the chain rule. And so the general power rule for integrals is the reverse chain rule. And basically it says, well, if I wanted to derive this function, well, the derivative would be 3x squared, right? But if I wanted to derive a function inside of a function, like 2x plus 1 squared, then I do the derivative of the outside function times, I am just like all over the place today. Okay, the derivative of the outside function with respect to the inside function times the derivative of the inside function, right? So in the end, my derivative has this little hook-on factor. It's got the derivative of this inside function, so you always see f prime. So in the end, you have, remember, like g prime of f of x. So you see the function in here, and then you see f prime of x as well. So you might imagine that if you see an integral that has like a function and its derivative multiplied together, that it's probably, ding, 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 it's probably a chain rule thing, right? Because you could just like go backwards. So you have to just think backwards and think, if I saw the function and its derivative, then I probably am going to go back to just like a composition of some type of function. So let's take a look at what that looks like. And you can imagine, let's just look at the examples. I won't try to do any more like abstract stuff. Let's just look. So we're going to differentiate this, and the derivative of 1 plus 5x to the 4th equals 4 times 1 plus 5x to the 3rd times the derivative of the inside, which is 5. So in the end, our derivative is 21 plus 5x to the 3rd. And that one might be a little deceptive because you're like, well, the derivative of the inside function isn't really there, but it is because the 5, see the 5 is right here, and we multiplied it by the 4. But say you saw something like that. You're like, oh, that looks like it has the derivative of the inside function. We can go backwards. So let's look at the next one. If we were going to integrate 5 times 1 plus 5x cubed, we see the derivative of the inside function is there, or the hook-on factor is there. So basically, we know that this is just the derivative of let's see, this is the inside function, and this is the outside function. So this would be our inside function stays 1 plus 5x. We add 1 to that exponent, and then we put it over that same exponent. Because then when you brought all of this down, when we derived this, we would end up right back in where we wanted to be. And, oh, plus c. Oh my gosh, I can't believe I forgot the cookies. Okay. So we hooked on the derivative of the inside of the power function, example 1, and then we had to like unhook it in example 2. So that's just the idea that when you see the derivative of a function, you can use this formula for the general power rule, and you can see that it's just the function u, which is a function of x, right? U would be any function of x. So, 3x plus 5, x squared minus 1, any of those functions are going to be, u. And if you see its derivative in there, we can just do this where we can just take u to the n plus 1 and n plus 1 on the bottom. So let's try a few of those. So I'll just tell you, this rule is not my favorite. I just like to do U-Substitution. And maybe we'll come back and we'll look at these with U-Substitution and see how they work just as well. In fact, they take a little less intuition. So let me just show you the reverse power rule, and then we'll come back and do them with U-Substitution as well. So we don't actually see the derivative of this function here, but the derivative of this function is a constant, right? So maybe that constant was like multiplied out already. Maybe that constant somehow, like when we did the multiplication, it had like a multiplicative inverse there. So maybe that's what was going on. So you can imagine that what would the derivative of the inside function be? It would be 3, right? So our original function should have had a 1/3 then, because that would give us so that when we did that hook-on factor, the hook-on factor would multiply by 1/3 and become 1. And so then our inside function is going to be 3x minus 1. Our inside function stays the same the whole time. We add 1 to the exponent, and then we put it over that. And that's it, plus c. There it is. That's the integral of that. So it's really just, f prime, or not f prime, f, the inside function stays the same, and then we just derive, or integrate the outside function, if that makes sense. Okay, so let's take a look at the other one. We do see the derivative, right? Let's think about in our chain rule. In our chain rule, we talked about like g of f of x. Okay, so our inside function is f and our outside function is g. So which one of these would be g, and which one would be f prime? Well, this one would definitely be, let's see, the derivative of this function. I'm pointing to it, but you can't see it. The derivative of this function is right here, right? So this would be f prime of x. And this would be g of x. Well, it should be g of t, shouldn't it? So that's g of f of t and g of t. So that means we derived this, and we had a hook-on factor. So our inside function is still g of t. kind of, yeah, this one's hard because it has a power of 1. Okay, so this has a power of 1 right now, right? And so this is now going to have a power of 2 over 2 plus c. And if we derive this, we could see that it would work out, right? We would bring the 2 down, and they would cancel out. And we would have t cubed plus t squared times the derivative of the inside, which is 3t squared plus 2t. So that's the reverse chain rule. It's just looking backwards. Let's try this one. Actually, we're going to do U-substitution on that one. Like, if you can see the reverse chain rule, awesome. If you want to work through the reverse chain rule on that one, that's cool. But then I want you to look at number 6, and I want you to decide if we can even use the reverse chain rule. And I'll tell you, it's a trick question. We can't, because is the derivative of the inside function anywhere? Right, f of x here, f of y, is y cubed plus 1, and then g of y g prime would be like something squared, right? And we don't really see the derivative of f of y anywhere. It's not like 2y is anywhere. So this one is actually not a reverse chain rule thing. And the only thing you can do with this one is you can just, you have to just multiply it out. So we got to square this. So we end up with not just y to the 6 plus 1. That's like the biggest mistake that everybody always wants to make. But you're going to end up with y to the 6, 2y cubed plus 1 dy. And then we just take the integral of each of those. So it's y to the 7th over 7 plus 2y to the 4th over 4 plus y plus c. And that can simplify just a tiny bit. Just the 2/4 is the only thing, yeah. So we have 1/7 y to the 7th plus 1/2 y to the 4th plus y plus c. And so we just had to do term-by-term integration on that one. So our next video is going to look at U-substitution and how that helps us get rid of that inner function so we don't have to do all this like heavy thought of like, what's our inner function? Do I see its derivative? It's actually really awesome. So come back in the next video for that.